B, C in is this part. So basically, we are now designing this as C in A or B plus AB. So that is this part. So you can see that this is A or B and C in, and this is AB, and this is the complementary path of that. And the other part, ABC in, ABC in over here, and then C out ABC, that is this part. So this generates carry first, and from the inverted carry, we find out the sum function. And this is quite popular because of the fact that we can make it very compactly. Now, one of the issues with circuit level design is that you'll have to think about the layout. So if you consider the layout and circuit, you'll find out that this implementation, which is there in the book, you'll find out it is shown by the book like this, and then they simplify that by moving this around actually. So basically they remove this connection and remove this connection so that it looks very much like this. So this is coming from the expression for C out is equal to C in A plus B AB, which is this part, C out bar, and then this part is ABC in, and then the A or B C in over here. ABC I is over here, and this part gives over there, and the C out is connected over here. So this requires 28 transistors, and we are generating carry out bar here, so we need one inverter over here to generate carry out. We are generating some bar here, and we need another inverter to generate some. So altogether 28 transistors are there. So I can throw out the inverters at output. So we have carry out bar here and some bar here. So it reduces to 24 transistors. So I'm just removing the inverters. But then your question is that how are we going to, so if I implement again in a straightforward way, I will use this one. I will generate the carry out bar, some bar, and then two inverters to complement them back. So again, as a circuit designer, you can see that when you are trying to generate with the full adder, so I have A naught, B naught, C naught. So this generates the inverted output. This generates the inverted output. Now, in this design, we put an inverter to make sum and carry. So now my question is that when I'm connecting the carry in of the carry out of that to the carry in, can I eliminate this so that I will be reducing an inverter delay? And this also, whether we can remove it or not. So when you are making a ripple carry adder, you can think of that. You can think of removing this and removing this. Because if I use use this configuration, I always will have the inverter delay on the caddy chain. So how do I make the caddy chain faster? By removing this. But if I remove this, then I'm getting the inverted caddy to the next stage, not the real value that I need. So I will try to, so this is the configuration after we eliminated the inverter. Otherwise it's the same number of transistors. Here we have 28 transistors because of this 4 and 24. So this is just redrawn, the same thing, the 24 transistors. We just eliminated 2 inverters. So if we do this, and we are calling it augmented mirror adder. How many of you have heard the name mirror adder? What is it? What is a mirror adder? Come on, read that book, 312. It is there, right?
It's an adder, and it takes advantage of like that inversion
Property.
principle, yeah. So like every other bit can.
What is the inversion property?
I think it's the odd bits can use the.
Okay, put your pen down. Just give me the expression for this. S A B C in and S bar, sorry, S A bar, B bar, C in bar. Who can give me the expression for that? That means what I'm trying to say is that I'm having a full adder here, A, B, C in, and I get C out here and S here. What is the expression for this? Which is equal to A bar B C in, A B bar C in, A B C in bar, or A B C in, correct? No, sorry. Sorry, this is wrong. This should be this. A bar B bar C in, A bar B C in bar, A B bar C in, and A B C in. This is what it is, right? Yeah. You're not sure? What is up? This is 0, 1, 1, 0, 0, 1, 1, 0, right? So what is this? This is equal to A bar, B bar, C in. This is A bar, B, C in bar, like that, right? So that is the expression for this. Is this correct or not? Are you guys okay or not? Now, if I try to find out A bar, B bar, C in bar, then what happens? Then this will be A, B, C in bar plus A, B bar, C in, I'm just complementing them. And it will be A bar, B, C in, and it will be A bar, B bar, C in bar. That means it's just the opposite of that. So in this case, this will be 1, this will be 0, this will be 0, this will be 1, this will be 0, this will be 1, this will be 0, this will be 0, this is 1. Correct? So what is this? That means this is equal to S bar A what does that mean? If I complement all the input bits, the sum gets inverted, correct? The same thing is true for the carry out. And this is the property, what is known as the inversion property. So, using that property, what I do is that I will come to this later. Relay calculation. So this is the inversion property. So if I complement the inputs, then the sum becomes inverted. Similarly for carry also, if I complement the inputs, carry becomes inverted. And I take full advantage of that. What I do is that I feed alternately the complemented input. So A naught, B naught, then A1, B1 bar, they are complemented, then A2, B2, and so on. Why am I doing it? Because I am now getting rid of those two inverters, which are unnecessarily delaying my circuitry in the carry path. I'm not so much bothered about sum, but I'm removing both to save some layout area. So this will be generating CO bar. Since all these are inverted, so this will be giving C1, and then this one will be giving C2 bar, and so on. Is this clear?